Okay, so let's start. So I corrected your homework, number 3, and you all fought very hard and you did well. And I know you have fought hard for many weeks now to follow this course and do well. So I thought it would be nice to you and that you deserve to have a slightly easier class today. So there will be no particularly major new theoretical developments today, but instead I thought I'd present to you, we'd have a bit of fun, I'd present to you the sort of Alfors classification, semi-formal classification of 5 types of real integrals that you can compute using residues, and that way you will, after today, feel much more confident. So whatever residue integral I throw at you, you will be able to say, I already basically know how to solve this because I have all the tricks I need in my toolbox, okay? So this will for sure be useful, and then for the rest of your lives you will just think residue integrals are easy. So this is the goal of today, and if you're already a champion of solving residue integrals, I mean, feel free to join in and help out, I mean, and give suggestions. So yeah, it's going to be a bit lighter. So the topic of today is different types of real integrals you can solve with the method of residues. Okay? So the idea is that Alfors, he says that there are 5 types. Okay. I mean, nobody says that it's impossible to come up with an integral that is not any of these 5 types, but what we claim is that if you know these 5 types, then you already know a lot. And no matter how much you know, there is anyway no guarantee that you'll be able to solve any kind of integral anybody gives you. But if you know these 5 types, you will be at a good, solid level when it comes to residue integrals. So this is, I think, a good motivation for trying to study these 5 types. So I will just go through them one by one in the order given by Alfors, because, I don't know, maybe he has some idea with what comes in what order. So it's in rough increasing order of difficulty, I suppose. So the first type is an integral of the following form. Cosine x theta. The first is an integral, a real integral of this form. So the integral from 0 to 2 pi of some rational function of cosine and sine with respect to theta. Okay, where q of x, so it's a 2-variable rational function. So it's a rational function. Okay, we assume that it has no poles on the unit circle. Okay? And this is important because when we want to integrate along our path, we don't want any poles to be on the path along which we integrate, right? We want them to be inside or outside, but not on the path. So this is why I'm asking no poles on the unit circle, because we're integrating here. This is like an integral along the unit circle, right? As you will see. So no poles on the unit circle. Okay, and an example would be, let me just take anything. Let me take the integral from 0 to 2 pi of sine cubed theta, why not? That's 1 plus cosine 7 yeah, whatever, something like this. So this kind of integral, so this you can solve with the residue theorem. And what is the idea to do this? So the idea is that we compute it using the substitution So what's substitution? Of course, there's one natural one. So we want to put z equals e to the I theta, right? So then theta goes from 0 to 2 pi, so this z will go one lap around the unit circle. This is the idea. So you put z equals e to the I theta, okay, then you get that, well, first of all you get that dz is equal to I e to the I theta d theta. You know how to do this kind of thing, right? So this means that d theta is equal to dz over I times z. Okay? And then you get that cosine of theta is equal to 1/2 of z plus 1 over z. And you get that sine of theta is equal to 1 over 2i of z minus 1 over z. So all of this seems to work out beautifully, and we are now integrating along the unit circle, hence why I ask no poles on the unit circle. So if I had in my denominator something that would be like x squared plus 1 or something, I might be in trouble. So just look out for that. Okay, so then what do we get? So we get... So I will write everything in sort of general form, because actually no matter what you have here in these conditions, you will do exactly the same thing. So you do the substitution, and then you will get the integral along the unit circle. So I write it like this, of q of this 1/2 z plus 1 over z, and let me write it like this, it's easier to see. 1 over 2i, z minus 1 over z. So you will get this, and then you get dz over I times z. So you get this integral, and then you see that this will be equal to, now by the residue theorem, this is equal to 2 pi I times, okay, so let's call this something. Let's call this now f of z, this new function, okay? So I don't have to write q of all of this nonsense every time. So 2 pi I, and then sum of the residues, so equals aj f of z times this n, well, let me just write it like this, over j, where aj are the poles of f inside the unit circle. I forgot the IC. Very good. Okay. What? I forgot the IC? Oh, yeah, right. Exactly. F of z over IC. Thank you. So I guess I can say that this is equal to 2 pi times this. Okay? But now I'm putting it back just to not to confuse you. But it's equal to this. So you see, you can compute this integral completely generally in this way, right? So this is the solution. So let's try an example, just to illustrate it also in practice. For example, let's say I want to compute the following integral. Let's call it IA, so it will depend on the parameter A. So I want the integral from 0 to 2 pi of d theta over 1 minus 2a times cosine theta plus a squared. And I want here a to be some complex number, but with absolute value strictly less than 1. So I want a to be inside the unit circle. So let's say I want to compute such an integral. Okay, so using this substitution, so we do as always, so we z equals e to the I theta, then we get that well, all the things that were before. So we get that IA is equal to the integral along the unit circle of dz over 1 minus 2a times 1/2, this thing. Okay, so 1 over minus a, and cosine is z plus 1 over z, okay, plus a squared. So you get this, plus, yes, plus a squared, and then dz over, I should not forget this, iz. Okay, so I should not forget that. Now we put all this together, we simplify it, and get that this is equal to 1 over I. And nobody likes 1 over I. Maybe you want to write it minus I. You know 1 over I is minus I. But okay, maybe it will be useful. Let me keep it like this. Integral along this unit circle of dz over, and then you try to simplify this, okay? So then you get minus a z squared plus 1 plus a squared z, and you get minus a. Okay, is that okay? So you get this. And now, what do I do? Next step. Sorry? Factorize. Ooh, factorize. Okay. So, how does this factorize? So, why do we factorize, by the way? Just to say it explicitly, we want to find the poles, right? So, on the poles of this function here, so we have this f of z. Let's define it to be 1 over this thing. Okay, so poles of f of z are zeros of this polynomial here. So minus a z squared plus 1 plus a squared z minus a. So zeros of this, the solution to that equation was there. Does anyone see how to factorize this? Anyone's very skilled in factorizing? What are the zeros?
It's a purely square root.
Yeah, of course everybody is able to do it unless you see it. I'm just wondering, anybody sees it? So it's equal to, this is supposed to be equal to this. Okay. It's equal to, well, I guess there is a factor of a as well. So it's equal to minus a times. So anyway, it's equal to minus a times this, and then it means that the poles, so the poles are z equals a and 1 over a. These are the two poles. Okay? And now, so we're integrating along the unit circle.
And what if a is equal to 0?
What if a is equal to 0? Well, then everything becomes very simplified and you will be able to deal with this. Okay, so let's assume a is not 0 here. Yeah, thank you. Yeah, why not? So if a is equal to 0, I'm sure we will see something. Then it's integral 0 to 2 pi of 1. So, okay.
No, I just wonder because we write 1 over 2.
Yeah. No. So if a is equal to 0, you go back here and you know the answer. And then you say a is not 0. Let's think. So if a is not 0, then is this. No, but it is good. We should be rigorous in mathematics. Okay, so poles are z equals a and 1 over a. So where are these? So this is 0, and if this is a, so absolute value of a is less than 1. So it's somewhere inside the circle. So of course, absolute value of a less than 1 implies that absolute value of 1 over a is greater than 1, right? So it's outside the circle. So it means that we have only one pole that will actually count, because the winding number around 1 over a will be 0. Okay, so this means that, so let me call this circle C, okay? So this means that winding number of this over 1 over a is 0, and therefore it will not compute. You remember that in the residue formula the winding number appears. So if you're outside, the winding number is 0 and it will kill the factor, kill the term. So therefore this one will not count towards our integral. It will count, however, is the residue. Oh my god. Excellent. Who is it? When z equals a. Okay, so when z equals a, we want to compute the residue of f of z. So this is the next step. And what is this residue? How do we compute it? So first we have to, so we found the poles, but we also have to determine what kind of pole it is. Okay, so in theory it could have been a removable singularity, but for sure it's not. And it's not an essential singularity, even though it could have been, in theory. But it's a so-called simple pole. It's a pole of order 1. Simple pole means pole of order 1. So that means that we can compute it by putting, formally we compute it by limit z goes to a of z minus a f of z. Right? But this is just equal to, because of the factorization here of the numerator, this is just equal to
1 over a minus a squared.
Sorry?
1 over a minus a squared.
1 over a minus a squared. Maybe. So, of course, you can cancel this one out. Actually, okay, so it's equal to this. But it's equal to, let me actually try to use something else. So you can do this. But let me also use this fact. You remember that if you have p over, you have residue of p over q. You remember if you have something like that, then this is equal to p of a over q prime of a, provided that this is not 0. So let me use that one instead. Because I saw in my notes I used that one. You can use either one. They're equally easy, but I think we use the other one more often, so let me remind you of this one. So this one would be then equal to, so p is 1, and q is whatever is down there. So it's equal to 1 over, and then we take the derivative of this thing. So the 1 over i is outside, so we forget about this for now, but we should remember it later. So it's minus 2az. Okay, and then plus 1 plus a squared, and all of this evaluated in z equals a. Is that correct? 1 over the derivative of the denominator. And this is then equal to minus 2a squared plus a squared. So it's equal to 1 over 1 minus a squared. So this is the residue in the only pole that is on the inside. So now we're happy about that. And now we simply have to write down that by the residue theorem, we see that IA, which is equal to this 1 over I. So, yeah, this is the residue. So we see that it's equal to 1 over I times this integral. We have over here. Okay, I don't want to really write it again, but I feel like you have to know. Minus az squared plus 1 plus a squared z, and then minus a. Okay, dz. So this integral is equal to, so the 1 over a is still there, and then times 2 pi I, sum of residues, but the sum of a residue is just now 1 over 1 minus a squared. only residue. So this is equal to 2 pi over 1 minus a squared, it seems. And is this what I got in my notes? Yes, it is. Okay, so this is the answer to the integral. So this is not too horrible, right? If this came on an homework or an exam or something, this you could do in less than 1 page, right? Or in roughly 1 page. And it could take you maybe 15 minutes, 20 minutes. Now, this is okay. So that was type 1. An example of that. Yeah, and you can note that, for example, sometimes it might not be, so the type was said to be from 0 to 2 pi, but if I give you 0 to pi or something like that, then you can often figure out how this relates to an integral over the interval 2 pi, because you know all these formulas for sine and cosine, I mean, how it behaves, how it is periodic, and how it takes its values on these two integrals. Right? So you can, if you get an integral from 0 to pi, you can often rewrite it as an integral from 0 to 2 pi, if you want to, and apply this method on the circle. I mean, there's no absolute law, of course, that you have to follow these methods. It's just a suggestion. But anything that works, basically. So, type 2. This was somehow not an improvement. But erasing this. Yeah. Okay, so type 2. So type 2 is an integral of the form minus infinity to infinity. So all the other ones except the first type will be from 0 to infinity or minus infinity to infinity. Okay, and now just of a rational function dx. So we're still in relatively simple territory here. So this is the second type. But it is worth pointing out what are the necessary hypotheses for a standard question here. So q of x is rational with no... What am I going to say here, by the way? Let's see if you can... 0 is no poles, you mean? Yeah? Yeah? No poles on? Very good. No poles on real axis. In other words, no real poles. Okay. No poles that are real. Very good. And I actually asked one more thing. Maybe this is more subtle. So let's see that this is equal to p of x over, I don't know, it's always hard to find a letter. P of x over s of x. So where the degree of the denominator, so you know what the degree of a polynomial is, right? So the degree of s is greater than or equal to the degree of p plus 2. Right? Plus 2. Greater than or equal to the degree of p plus 2. Okay, and this is for convergence reason. Now, let's assume this. To calculate it, with residues, let us consider, you consider always this type. So you consider minus r to r, and then you consider the half circle here. So this is IR, this is minus r, and this is r. So you consider this. Yeah, let me draw it in color. And this one goes, so always counterclockwise. Okay? So you consider this contour. And so the half circle. Let's call this half circle CR. Okay, where CR is equal to, it splits in 2 parts. So, yeah. So I'm going to be confused, by the way, about what I call all these parts. I'm going to change this notation all the time. I wish I had some canonical notation that I really liked, but it's going to be what I happen to say it is, unfortunately, when I write it here. You can, of course, name it whatever you want. Or maybe one of you has a favorite notation. What should I call it? I never know. I want a name for the total path, I want a name for this part, and I want a name for this part. The line. So, maybe CR should be, CR is not the whole path. CR should be like the half circle. CR should be the half circle, and then the whole path should be gamma, but not just gamma because it depends on R. So it should be gamma R. Okay, and this should just be the interval minus R to R. So gamma R is equal to CR plus the interval minus R to R. Let's put it like this. And plus, of course, means that you do first the path and then the other. I mean, when I write like this, sometimes I would write maybe, if I took the path in the other direction, I would write R to minus R. Even though that looks strange. You're not used to be writing sets that way. As a path the direction matters. Where you could write minus R to R. Anyway, I do it like this. And then yes. Exactly. So now, first thing to notice is that Q of Z, so now it's obvious what Q of Z is, right? So it's if I put Z equals X plus IY, then you get that dz is equal to dx, and you consider the integral along gamma R of Q of Z dz, okay? So you do this, and then you see that that Q of Z, it's still a rational function, so it has a finite number of poles, of course, because it's just the zeros of the denominator, which is a polynomial.
Z is equal to X plus IY.
Yeah.
And Z is equal to dx.
Yeah, I mean, you see what I mean. You consider, let me just put it like this. Consider where you have replaced every x by z. Let me put it just that way. So you know, for example, you should think of, if I want to integral minus infinity to this, if I want to integrate something like that, then I will replace it by the integral along such a thing, gamma r of z squared over z4 plus 2z plus 1 dz. Okay? Yeah, and then of course, what you want is the part, when you integrate this function, this complexified function, when you integrate it along this part of the contour, that is the real line, then it takes exactly these values. Right? So this is why what we want is this part of the integral, but because the residue theorem applies only to a closed contour, we have to do something to close it, and you can do half circle, you can do whatever you want, but you would like to do something that you can work with, so you choose a half circle. You could try a triangle, or you could try a rectangle, but you should definitely try something simple. And this is the canonical choice. So this is the one I present to you anyway. So since it has a finite number of poles, this integral along the full curve of Q of Z dz is equal to 2 pi I times the sum in the upper half plane, so the imaginary part is greater than 0, of residues of f of 0. Okay? sorry, FZ, QZ. Residues of QZ. So of course there is a finite number of poles in here. Here, here, here. There are maybe some poles here. But anyway, for R large enough, this will be equal to that. So I have to write for R large enough. Okay. So most of these residues will be 0, of course, except the finite number, which will be equal to this. So you look for the poles in the upper half plane. On the other hand, what we want to do, so it's clear that this is what we want. Okay, so now we compute this whole thing, and it includes part of what we want. But we have to also see what this part on the half circle does. And this is often the trickiest part. I mean, if you have problems with something in a residue problem, it's usually to estimate the parts that you put that you don't want. Okay? If you manage to choose the contour correctly, now you need to know how to do the estimate. Typically, these parts will tend to 0, but not always. So you have to be careful. Okay? So in this case, on the other hand, okay, let's see how we do this. So we integral along this part of Q of Z dz. So now we want to estimate, we want to show that it actually goes to 0 as R tends to infinity. So how do we do it? When we want to show an integral is 0, in complex analysis we take the absolute value and show that the absolute value goes to 0. This is the trick 99.9% of the times. So we see that this is less than or equal to, and then we do this little trick here that we say, I mean, there are many ways to try and wing this, but if you want to write it nicely, you can do this. You can write z squared over z squared. Okay? Multiply and divide by the same thing, so far done nothing. And then you say that this is less than or equal to the supremum on this z equals r of, then you look on the one hand on this, and then times the remaining part, dz over absolute value of z squared along this circle, CR. You see what I did, right? I move the absolute value inside and then I divide it in this way. Okay, but now the point is that this one, what can we say about this one?
Bounded.
Exactly. So this one is bounded for R large. Okay? So everything is for R large. So if you have some problem with R being small, you don't care. You just say, okay, R is larger than whatever gave me a problem. So, because of course this is thought of it being an immensely large circle. We want R to go to infinity. Or half circle. So then this is less than or equal to m. And then this integral here, what does this one do? So it's less than or equal to 1 over r squared. Okay? This is what I want to do, right? 1 over r squared times 2 pi r. Actually pi r, because I'm just on half the circle line. So pi r. And this is equal to m pi over r goes to 0 as r goes to plus infinity. Okay, so that wasn't very hard. But still I think it's worth seeing. I think it's nice to write it this way somehow. I don't know. At least, maybe now it doesn't matter so much, but because otherwise you have the tendency to somehow wing it and say, oh, because the order is somehow, something goes to 0, but this is somehow 0. Okay, anyway, this is the part where you should take a little bit of care in the more difficult exercises. This one is still easy. Okay, so this one goes to 0. So of course here you should note that I used the assumption on the degree, right? I used this assumption that I wrote somewhere. This I used here. So if this is not true, then you have to beware. So maybe if I was very mean, I could give you a trap some exercise like that where this condition was not satisfied, and yeah, it would be a trap. I don't think of myself as very mean, but you never know. So now, what does this imply? So this implies that the integral from minus infinity to infinity of q of x dx is equal to 2 pi I times the sum of the residues of this q of z. Quite simple. Where this is over imaginary part of the greater number. I changed notation for my residues also all the time, but you see what I mean. So all the residues in the upper half plane, you compute them, you sum them, and you're good. And how do you compute the residues? You just find the zeros of the denominator to find what the poles are, you see what order they are, and then you can use this business here, typically. You just derive the denominator, you take p of a over q prime of a, and then you get this. Okay, so I had an example, but it's not so important. We have more important examples to do. So you can go back to that. Because I think all of you can do this, right?
I have a question.
Yes.
We could almost do the same, but instead of taking the upper half, we take the lower half.
Yeah, sure.
And then the residues of the upper half is equal to the sum of the residues of the upper half is equal to the sum of the residues of the lower half, almost, because they both should equal to the integral from minus infinity to infinity.
Yeah, so we just have to be maybe a little bit careful about.
I mean,
yeah.
we can find rational functions with
poles only and
only on the upper half. So this is strange.
What is going on?
Maybe there's something considered.
Sorry?
It should be, but it's still strange. I think the proof of the other side. I mean, if we do, we can do the same, and I think the proof will work, right?
Yeah.
Yes, all the zero are conjugated because it's a real polynomial in the denominator. So
Yeah, that's a good point. Thank you. Yeah, that is true. So it does make sense. Thank you.
And I think view that is not necessarily rational because we only relying on this condition, the supremum of bounded.
Sorry, say again. So this condition you're talking about, or no?
Not this condition, and I think Q that is not necessarily rational. I think it only says if it satisfies the supremum bounded, then I think it's again true. Yes.
Yeah. Well, maybe let's not generalize too much, but for sure there are other cases where this kind of thing holds. But we're only on classification number 2. Okay. So there are other parts where you do similar things. So, I mean, because in theory other things could happen elsewhere, but yeah, similar things for sure happen. So, do you agree that you don't need an example? If you need an example, then please tell me, and I can do it. But otherwise I go on. So the third one is an integral of the following form, minus infinity to infinity of q of x times e to the I alpha x dx, where alpha is a real number, okay, and q of x is rational with no real poles, as usual, and q of x is p of x over S x, where degree of S is greater than or equal to degree of P, but I believe it may be enough with +1 here. So there is a little difference with this E factor might. Okay, now someone will tell me, oh, but if alpha is equal to 0, then it's the earlier one and it has to be 2. So, sometimes. So, sometimes enough. Okay. Just to dodge this bullet. Now, so we're talking about an integral like the one we saw last time. So, for instance, integral e⁻x over x squared plus 1 dx. X squared plus 1 is always nice because it's the easiest one where you know the roots are not real. It's I and minus I and you can visualize everything. Okay, so what you do to solve this is that you use Q of z. So look at this. Q of z is equal to, for example, equal to z squared plus 1 here. Okay, something like that. So now I'm doing somehow the example in parallel with the general theory. And then you note, you use again the exact same semicircle. Okay, so this is a very common semicircle. Minus R. Okay, you use this. And we use the same notation. Try to keep the same notation for the circle. Then we see that so by this time you use by Jordan's lemma. So I guess this is the difference now, but earlier we just did it by hand, now you use Jordan's lemma. So it's a bit more complicated. Okay, and Jordan's lemma actually applies to alpha greater than 0. So let's assume now alpha is greater than 0. So then you have Jordan's lemma. Then this one gives you that the absolute value of the integral along this semicircle part of Q of x at dpi alpha x dx or dz, whatever, I don't know why I put x. So this is less than or equal to, do you remember what it was? Yeah, I hear a pi over alpha. And then there is something else? MR. And what is MR?
And is the maximum.
Of what? Of the whole thing? Of the cube. So MR is maximum of the absolute value of Q. And maximum over Z on this semivector. So this is what you have. But, there's also this. But this thing here, MR, what does this tend to? This tends to 0 as R tends to infinity. And this is true if degree of S is greater than or equal to degree of P plus 1.
Here theta is 1 over c squared plus without.
Sorry, theta is 1 over c squared?
Use q theta.
Yeah.
1 over or e just.
Now I was just writing q of z. I don't understand. What?
The formula above is the integral of q of x times e I alpha x.
Yes.
So the q of x is only the rational function.
Yeah. Thank you. Yes, indeed. Great. So of course you will consider this function that I wrote down, but the one I wanted to call q of z was indeed this thing. Okay, so this thing goes to 0, and it means that the integral along CR of this whole thing goes to 0 as r goes to plus infinity. Okay. Yeah, if there is no ambiguity, really, then you could be allowed to write things like this, at least for me in class, because I can tell you orally what I mean. Now, so what remains? So what remains is that you look at the integral from minus r to r, and this one, of course, tends to the integral that we want. So, this integral is equal to the sum from k equals 1 to the degree of s, which is the number of poles, 2 pi I, of the residues q of z e to the I alpha z. Okay, so the residues of this function, where zk are poles of q of z. I mean, they are poles of this thing, but they are the same as the poles of just q of z. No? Because this one does not add to it. This is just a holomorphic function. So it doesn't add to poles. Okay, so now I also prepared an example of this. Do we do it? Yeah, I think we do it. Let's try to do an example. So we already saw an example of this, right? I computed essentially one residue so far in class, and it was of this form. It was exactly this one, in fact. So I just want to give you the following. Yeah, so we already computed that one. Do you remember that we did that? So this is how I introduced Jordan's lemma, was by computing this. So example, if we have two integrals, let me define I1 to be the integral. Let me just point this out. So this is cosine x, the x squared 1, dx, and I2 is the integral of sine x over x squared plus 1 dx. Sorry if I overuse x squared plus 1, but as a denominator. Then these two integrals are, in some sense, of this form, right? Because we have the real and imaginary parts. So if I ask you about these, you can compute that, and then you get both of them for free. I mean, I could ask only one of them, but you automatically get the other as well. Just by seeing the imaginary part. So I1 here, so note, I1 is the real part of this integral. This is very strange. Well, okay, and I2. Okay, so we have this, and then we already saw so if you just go back in your notes, we did show, I hope you agree. You agree, right? We did show this. That this integral is equal to pi over e. Okay. Of course, you can, as an exercise, do it again. Try to check it. This is equal to pi over e, which is interesting because it's real. So this is real. Now, what does this mean? It means that I1 is also equal to pi over e. And I2 is 0. So this is what we need. This is what you get. Okay, and now this is important. Now we're getting into the more subtle things. So that's the end of that example. So this was type 3. Now I will give you an exception to type 3. Okay, so example 2. An exception to the standard method is when we have a simple pole at z equals 0. Okay? So we said you have no real poles. But let's say actually you have one real pole at z equals 0. Okay, so the example I want to take is the following. So let's take minus infinity to infinity, or 0 to infinity, actually it's the same, of sine x. Yeah, so you see when I wrote down the type, I wrote down minus infinity to infinity. But if you were to see at some point in your life, during exercises or exam or whatever, 0 to infinity, don't be scared and think, oh, it wasn't the type. You know, you can do essentially the same. You see that this integral is twice the integral from 0 to infinity. So really it's the same. So especially with trigonometric functions, you can very often relate, you know, this is an even function. So I can put minus infinity, or I can put 0. Also works. So take notes on that. So how do we do now? So this doesn't quite fit our assumption because it has a simple. So you consider, of course, this. So the problem is that this f of z.
Actually, that's not a pole.
Yeah, actually it's not a pole, I know. It's a removable singularity. Yeah, I had also thought of this before. But, so actually the problem is that E of IZ over Z, if you try that method, because, you know, that method says that if you have cosine and sine, you should try to integrate E to the IZ. Okay? So this one has a pole. That's a simple pole at z equals 0. Okay, and what is the business with this fact that sine x over x, sine z over z has a removable singularity, so it's analytic? When I tell you yes, that is correct. It does extend to an analytic function. So when you take this kind of half circle path, then what will happen is actually that, okay, the integral along this whole business has to be 0, because you're actually integrating an analytic function. But then, in this case, it actually remains to understand this this part on the semicircle, and computing it, and computing these various things. And so in order to do this, actually you might as well somehow do this one. I understand this is not great motivation, but another way to put it is that let's do this one, because I might have asked you about cosine x over x, you know, something like that. Or I might have asked you for e to the ix over x. Okay? So either way, with the standard method, this is a problem. So yes, sine z over z extends to an entire function. But let us still compute this. This is now my claim. Okay? Because I want to show you that you can deal with this one. Is it clear? I'm saying because this one has a removable one, you don't have to consider this. But if you were by such a standard method, you can still do it. Well, let me show you how you still do it. So, you consider the following contour. So now the problem is, so you would like to take the same thing, okay? But you can't, because you have now, if you integrate this function, then you actually have a pole here. This is not the removable singularitity any longer. So when you consider this function, it has a real pole, which is order 1. So you are not allowed to have a pole on the contour you're integrating. So what do? Well, simple. You go around it with a small circle. Okay? So this is now epsilon, and this is minus epsilon. And this is a small circle. And now we should try to keep our notation consistent. So this one is CR, is the big half circle. Then you have a small half circle, which I guess should then be called C epsilon. Okay? And then you have the total thing will be gamma. And you will write this total, actually gamma R. And gamma R will be CR, and then you will go minus R to minus epsilon, and then you will go really minus gamma epsilon actually. Okay? Minus gamma epsilon. Sorry? That's C epsilon. Minus C epsilon. And then plus epsilon R. Okay? So this is our path. And of course, so with the notation C epsilon, it should be counterclockwise. So that's why I write minus. Okay. This is, you have to keep track of it, but the notation is just try to write something that makes some kind of sense. That is natural. Okay. Now, by the way, you have no poles inside. Okay? So this here is the only pole. So no poles inside of this function. Okay. So what you get is so you get that the integral along this whole gamma r f of z dz is equal to 0, like we said. Okay, so if we had integrated sine z over z, we could have done without this little thing. But now, with this one, we have to do a little lap around. Okay? And now, what we get is we have to estimate now the different parts. So we're interested in the sum of these two parts. Actually, they are the same, right? The integral here is equal to the integral here. In the limit, at least. But actually also not in the limit. So we're interested in these integrals. So we have to estimate what is left over, the small circle and the big circle. So now we do the big circle. So on the big circle, we have integral of CR of this f of z. So f of z is this, by the way. I hope it is true. F of z is that. So the integral of this, so this goes to 0. Let me just write it this time by Jordan's lemma. Okay? So you can check this. Check. Now, the small circle, no, the straight paths, let's do them first. So the straight paths are, here you have that the integral of minus r to minus epsilon of e to the ix over x dx is equal to minus So I just write it in a more normal way. So it's equal to minus e to the minus ix over x dx. So really now if we recap, we have that 0 is equal to the integral of CR minus the integral of C epsilon plus the integral of epsilon to R of e to the ix minus e to the minus ix over x dx. Okay. So we see we have this. And now I also have this in the small circle. Okay, so not only did I deal with the straight path, but I also recalled to myself what I had. I had 0 is equal to the total integral, which was, of course, the sum of these things. This is often helpful to take stock and remember what you have already when you count residues. And now the small circle. How do we deal with the small circle? Now we don't have a Jordan's lemma or something for the small circle. So now we actually will compute it. So here e to the iz, so it's equal to 1 plus, I mean we know what it is. Okay? So e to the iz over z is equal to 1 over z plus h of z. So basically we know the following.
How did we write A or IZ in this form?
E to the iz? Yes, I mean, just to look at the Taylor series expansion and you just see what h is, basically. So, what we get is that the integral along this C epsilon, okay, I will care later about minus this, but let me forget the minus for the moment, of e to the iz over z is equal to the integral over C epsilon of dz over z plus the integral of C epsilon of h of z dz. Okay? So now I do this. And this one goes to 0 as epsilon goes to 0. Because what is the reason for that?
It is bounded in a
Yeah, simply it's continuous actually. This continuous is enough. Because h of z is continuous. It's even analytic. So in particular it's continuous in this neighborhood we found. Now, dz over z, so continuous is 0. Now, the other part, for this part, we write z equals epsilon e to the I theta, where theta goes from 0 to pi. Actually later we'll be interested from pi to 0, right? Now we calculated this one. So it goes from 0 to pi. So this means that the integral of C epsilon dz over z, we compute it, it's equal to integral from 0 to pi of 1 over epsilon e to the I theta times the derivative of this, d theta. Now we go back to the first definition again that we had. This is the first thing I taught you about integration. Epsilon. Thank you. And these cancel, of course. So this is equal to I times the integral 0 pi d theta, which is equal to pi times I. Okay? And this means that minus the integral of C epsilon of this thing is equal to minus pi I. And this is what I was interested in, right? Okay, so now from this business, we do it in orange. So this implies that, so what do we get now? Right, so this is 2i times sine over x. Okay, so let me write this. If we now are interested again in this 2i sine over x thing, then this thing here, so this is equal to 2i integral of sine x over x. Okay? So we get that 2i integral sine x over x, where this goes from epsilon to r. So this is equal to integral along C epsilon minus integral along CR of the appropriate things that we had here, right? Which was this f of z. Okay, so integral f dz. And we already computed that this tends to pi r, and this tends to 0. Okay? So in the limit, this whole thing tends to 2i, so 2i times whatever we want tends to pi r. So this implies that the integral of 0 to infinity of sine x over x dx is equal to pi I over 2i, which is pi over 2. Okay? And if I wanted the integral from minus infinity to infinity, it's equal to 2 times that, which is equal to pi. Okay? And let me write it. Because this is an even function. Okay? Now, that was number 3. The first 3 are, okay, this was an exception where you have to do a smaller circle, so this is useful to see. Now we're going to see number 4. Number 4 and 5 is where it gets interesting. Okay? Because number 4 and 5 is where you have to deal with branch cuts and branch points. Oh no. Okay, so consider this integral from 0 to infinity of something of this form, x alpha q of x dx. Okay, where alpha is a real number between 0 and 1. Strictly. So, of course, for example, this could be the square root of x, or the cube root, or something like that. And q of x is a rational function, where degree of s satisfies the usual condition, and it has no poles on the positive real axis. Okay? Because this is where I'm integrating now. Okay, so it can have poles on negative real axis if it wants. So, for example, this could be integral from 0 to infinity of square root of x over, let's take this time, x4 plus 1. Okay, so it could be something like this. And the square root, as you know, is not single value. So the difference So big difference. Now we have branch points. So we have to deal with this. So of course the first thing whenever I integrate something like this is to define, make sure I always define what branch I am working in. Okay, so let's have some sort of initial discussion. So, okay, so choose a branch. So choose a branch of z to the power alpha. Okay, so I'm dealing now with the general case. So it could be x to the cube root or whatever. Like in my homework, by the way, I have a cube root. And then z to the alpha. So how do you define it? Well, it's e to the alpha log z. This is the way to define it. Where log z, so it's still not specified because log z is ambiguous. So I tell you it's this, and then I have to be precise about what log z is. So where I choose log z to be log of absolute value z plus I times argument of z. And now I still have to tell you what the argument is, and then I will have been precise. Where the argument of z, this is the key line, I will choose it to be now in 0 to pi. So this is not the principal branch, okay? So this is the key line. This is what will make you lose many points if you forget. Okay, so so not the principal branch. Okay. So now, so I told you that okay, we have a principal branch, but sometimes it's useful to choose another branch. This is exactly such a moment when you would like to choose another branch. Okay. So now I cut away the positive half axis. This is what I cut away, and my domain is then all the rest. This is now where I define my square root function. So it's defined here. Now, pick an x here. So as I told you, this is now the initial discussion. I will try to tell you what is going on. So now, if we approach the real axis from above, okay, then the value of such a point here we have z is equal to e to the I theta, but theta is very small. Well, it's some r, why not? But it's equal to e to the I epsilon. Let's say where epsilon is very small. Okay. So yeah, it's equal to this, and this is actually equal to, well, it's equal to this. Let me just put it that way first. And, well, actually what I want, let me write it like this. So here, when I approach it from here, z to the alpha is equal to e to the alpha log z. And that's right. So this is what I wrote, e to the alpha log z. But this is equal to e to the alpha log modulo of z, okay, plus I epsilon, something very small. Now nobody can see anymore, I guess. Okay. So, sorry, z to the alpha is equal to e to the alpha log z plus I epsilon, and this tends to e to the alpha log absolute value z, as epsilon now goes to 0, right? This angle goes to 0. So this tends to this, which is equal to, now this is the real logarithm. You remember this. So log, I define it as a branch if it is a complex number, but when it's a real number, there is only one logarithm. It's the usual one. So now there is no, now these are all real numbers, so now there is no weird thing going on. So now you can safely say that this is z to the power alpha. Okay? So if z equals x to the plus I alpha, and this tends to x, that's x plus iy, this tends to x on the real axis from above, okay? So here y is greater than 0. So then z to the alpha tends to x to the alpha. Okay? So far so good. But something happens if we approach it from below. And this is the tricky part, the important part. And actually it seems like it's something that should be a bad thing, annoying, but it's exactly what allows us to evaluate these integrals. We will see later. So this is from above, so to speak, when you approach the x-axis from above. So from below, okay, so z equals x plus iy, where y is now negative, then if this tends to x, okay, so y tends to 0 from below, to 0 minus, okay, then z to the alpha is equal to e to the alpha log 2 pi minus epsilon, something like this. Well, actually, the absolute value, but let me do this. So e to the log z plus I to 2 pi minus epsilon, and this tends to e to the 2 pi I e to the alpha log z, which is equal to e to the 2 pi I, sorry, alpha, 2 pi I alpha, thank you. 2 pi I alpha, e to the alpha, so e to the 2 pi I alpha, and this is just real now, all numbers are real, so this is the usual logarithm, absolute value of z to the alpha. Okay, so this is equal to now e to the 2 pi I alpha times x to the alpha, because this z was tending to the real line. So this tends to x to the alpha. So you see, these are not the same values. So from above, it tends to x to the alpha, but from below, it tends to e to the 2 pi I alpha, x to the alpha. Okay, and these are different values. These are different values. And this might seem like a problem, okay? At least it's actually not going to be a problem, it's going to help us, but it's definitely a phenomenon that has to be taken into account. Okay, and it's what helped us. So, to compute this now, to compute the integral, consider a keyhole contour. So this is a keyword. So you have this axis where it's not defined. So far you have seen after this one you will have seen all the contours that you usually use, maybe except for sometimes you use a rectangle or something like that, or a square. So you remove the real half-axis. Then you take, so what you do is you start a little bit above, at R, okay? Start a little bit above, and you go around in a circle. Yeah, this is always hard to draw. My keyhole contours look like a mess. Then you go all the way around, and you stop a little bit before you go back. Why do you stop before and start before? Well, because technically you're not allowed to be on this branch cut. You stop a little before. Now, then you go in, because you want to make something closed. So after all, you have to go around this thing that extends to infinity, right? So your only choice of going around it is you have to go left. Now, you go, once you arrive here, actually a little bit before, you follow, so there is a small circle here, okay? And once you hit this of radius epsilon, and once you hit this circle, you follow the circle. And then you draw this line to go out again. And this is the keyhole contour. So this is a circle of radius epsilon, this is a circle of radius r, and then you have these two lines here. Okay, so now you might ask me something like, oh, but what is the distance between the real axis and this thing? If the radius here is epsilon, maybe this is epsilon times the square root of 2 or over square root of 2 or whatever. I don't care. When epsilon goes to 0, this distance goes to 0. Okay? We don't need to make it explicit and choose an angle. If you want to be super rigorous, you can. But I mean, this is just being over rigorous. It's very clear. I mean, check once in your life that it actually works, and then don't write it every time. So it's clear that this distance goes to 0. Now, so what I'm doing here, the way to think about this works, but it's not immediately clear that it has to work. But this is still the way that we will do it. So the thing is now that, okay, let me call this L1 and L2. L for line or linear or something. So these two lines. So they go, of course, in this direction. Then you go in this direction. Then you go around like so. And then you go out along this line. Now, to see what you do is that the contribution from L2 and then L1, what is the contribution? So let us see. So contribution, so intuitively, and this is sort of a keyword, but intuitively, as epsilon goes to 0 and r goes to plus infinity, so we shrink the inner circle and make the outer circle large, then this integral of L1 plus L2, okay, so I follow this one in this direction and then this one in that direction. So the point is that they will not cancel, right? So normally so these lines get closer and closer to each other, and if the function we're integrating was actually continuous, then they would just cancel, because one goes in this direction and the other one goes in the other direction. But now they won't, because when I come from below, I pick up an extra term, right? Then I have this. And when I come from above, I have this. So this will be like the integral of x to, first you do the x to the alpha, but in the minus direction. So first it will be minus e to the 2 pi I alpha, x to the alpha, dx. Okay, so actually I should say that it tends to this, right? So intuitively it tends to this. It tends to the integral from 0 to infinity of minus e to the 2 pi I alpha, x to the alpha, and then the other one you do it in the plus direction. So plus x to the alpha, all of this dx, which is equal to 1 minus e to the 2 pi I alpha integral from 0 to infinity of x to the alpha dx. And now, so I realize I forgot our q of x here. So if I put a q of x, then I can just put in a q of x here, q of x everywhere, and it will tend to x to the alpha times q of x dx here, because it's just linear. So this thing will tend to this, and then what is left is to show that along the big circle and the small circle, they tend to 0. Okay? And then, of course, the last part, after you're done with that, is just to compute the residues of this whole thing. Okay? So then estimate integral along CR of this z to the alpha q of z dz, right? And integral of c to the epsilon of the same thing. Okay, and usually these, so where epsilon goes to 0 and r goes to plus infinity. So you need to do that, and usually this will go to 0, and then you use residue theorem. Okay, then use residue. Of course. So, example. Yeah, I'm a little bit in time trouble, let's put it that way. But let's still do the example. Square root of x over x squared plus 1, yes, x squared plus 1. So we know what the poles are. Okay? So we do all of this. So we say that the square root of z is equal to e to the square root of absolute value of z, e to the I argument of z, where argument of z is in 0, 2 pi. We consider the keyhole contour. Okay, then we consider f of z, which is square root of z with this one I just defined, over z squared plus 1. This has simple poles at z equals plus minus I. Okay, and we compute the residues. And when you compute the residues, you have to be careful, by the way. So you see that 2 pi I times the residue at z equals I of f of z. So it's equal to, so you compute them. And here you have to be careful to use the correct branch of the square root. Right? So it's equal to, in this case, so you use this limiting formula. So it's equal to 2 pi I limit z goes to I of z minus I square root of z over z minus I times z plus I. Let me just do one carefully. Which is equal to 2 pi I times the square root of I over 2I, which is equal to pi square root of I. And now we just have to be careful what is the square root of I. Okay? So this is where you have to be careful. I mean, now it's okay. But I is equal to e to the I pi half in this branch. So this is equal to pi e to the I pi over 4. Okay? And then you have that 2 pi I times the residue at z equals minus I of f of z. So check this, that it's equal to minus pi e to the I 3 pi fourths in this branch. Okay? In this branch. Moreover, we now estimate along the circles, so the absolute value of square root of z over z squared plus 1 dz. Now we have to estimate this. So this is the last instructive moment that I want to show you before I stop, okay? Sorry for going a little bit over time. So now we do the same trick as before. So this is equal to, well, it's less than or equal to the integral of z equals r of absolute value of z squared over z squared plus 1, and then times square root of z over z squared plus 1. Sorry, what am I doing? Over z squared. Okay? So this, and then dz with absolute values. So I just multiply and divide again by z squared. Okay? And then this thing here is bounded for r large enough. So then we get that this is less than or equal to m, and this is square root of r over r squared, and then the length of this whole thing, which is 2 pi r. So, yeah, because it was a full circle now, so it's 2 pi r. And this is equal to m over square root of r times pi, times 2 pi. Maybe. Is it? Yeah. Anyway, this goes to 0 as r goes to plus infinity. You see? And here, of course, we use the fact that the degree of the denominator was at least 2 larger than the degree of the numerator. Okay? So we have that. We can do a similar thing on the small circle, because we also have to do the small circle, of course. So on the small circle, we have absolute value of this c epsilon, square root of z over z squared plus 1 dz. This is less than or equal to the absolute value, the integral over this, the value of z over z squared plus 1 times square root of z over z dz. Now this one is clearly bounded from above, because okay, this goes to 1. So this is less than or equal to this small m square root of square root of epsilon, sorry, over epsilon times 2 pi epsilon, which is equal to 2 pi square root, 2 pi m square root of epsilon, which goes to 0 as epsilon goes to 0. Okay? So, finally, let's put it all together. So when you compute residues, it's a lot about remembering all that you have. So finally, we get that square root, this integral that we were interested in, is equal to, so 1 minus e to the 2 pi I alpha, right? But alpha was equal to 1/2 here, because we're doing the square root. So this is I pi, okay? So this is but of course you don't have to remember this by heart. You can always do the same thing to find it out again. Okay? So you do this, and this is equal to 2 pi I times the residue, let's say equals I, of this f of z, plus residue of z equals minus I of f of z. Okay, where f of z is the obvious thing. This whole, I defined it somewhere, I hope. Yeah, this is f of z. So this was equal to, and this is equal to, which gives us that this integral square root of x of x squared plus 1 dx. So this is equal to actually 2. Okay? This is equal to 2. So it gives that this integral is equal to 1/2 times, and then I have the 2 pi I computed not the residues, but I computed 2 pi I times the residues already. So it's equal to this times, and then I have to sum, so pi e to the I pi over 4, and then minus pi e to the I 3 pi 4. Okay, and this is equal to, so we don't want to leave the answer like this, okay? So please try to write it in standard form or simplify it. So this is equal to 1 plus I over square root of 2. Okay, this is equal to minus 1 plus I over square root of 2. So when I sum them together, I get, so 1 minus this actually. So I will get 2 pi over square root of 2, I think. Right? See? Yes? Is equal to 2 pi. So if you do 1/2 from here, times 2 pi over square root of 2, which is equal to pi over square root of 2. And this is also what I got in our notes. So this is the final answer for the integral. Okay. Now, sorry for going over time.